In early March 1943, deep inside the roaring industrial heart of the American Midwest, the Fisher Body Plant No. 2 in Grand Blanc, Michigan, echoed with the rhythmic crash of steel presses and the hum of welding torches. The air was thick with smoke and urgency. America was in the second full year of total war, and the arsenal of democracy was straining at every seam. But at Fisher No. 2, a quiet crisis was unfolding that threatened to derail one of the most important production programs of the entire war: the Sherman tank. Each morning, shift foremen watched as workers struggled to mount freshly built turrets onto their hulls. The turret, the massive rotating assembly that housed the 75mm cannon, had to fit precisely onto the hull's circular turret ring. The fit was supposed to be seamless, smooth, exact to a tolerance of 0.006 of an inch. But it wasn't. Turret after turret was being rejected because the ring wouldn't align, wouldn't rotate properly, or locked up completely. In the language of the plant floor, they called them fighters, turrets that fought against being installed. Every fighter was a day lost, a crew delayed, a war machine stalled before it could ever leave the factory floor. By March, more than 1 in 8 turrets were being rejected. Entire shipments sat idle, waiting for rework. Managers tore their hair out trying to understand the cause. Engineers blamed the welders for heating the steel unevenly. Welders blamed the engineers for poor blueprints. The Army Ordnance Department blamed both. The situation wasn't unique to Fisher. The same reports were coming in from Chrysler's Detroit Tank Arsenal, from the Pressed Steel Car Company in Pennsylvania, from Pullman Standard in Illinois, and from Lima Locomotive Works in Ohio. All across the country, tank production, the backbone of the Allied ground war, was being choked by one maddening, microscopic problem: the turret ring. The irony was bitter. The United States had out-engineered the Axis in so many ways: faster aircraft, more reliable engines, a logistics system the enemy couldn't even dream of. But now, at the peak of its industrial might, it was being slowed by a steel circle just over 5 feet wide. At Fisher Body Plant No. 2, Superintendent James Morrison could feel the pressure every time he picked up the phone. Washington was demanding numbers. The War Department wanted 48 completed turrets a day, 1,140 a month, and Morrison's factory was barely managing 1/200. His engineers tried everything. They redesigned clamps, changed weld sequences, adjusted preheating methods. Nothing worked. The rejections kept coming. Meanwhile, Army production inspectors were beginning to warn that the delays were cascading. If turret deliveries didn't improve, the Army's schedule for tank shipments to North Africa and the United Kingdom would slip, jeopardizing the buildup for the planned 1944 European invasion. The situation was dire enough that Army Ordnance held an emergency meeting in April 1943 to discuss turret misalignment phenomena. The official memo circulated that month read bluntly, "An excessive incidence of turret ring distortion has been noted across multiple facilities, resulting in costly rejection, remachining, and delivery delays." While the generals debated, a quiet, unassuming man on the third shift at Chrysler's Detroit Tank Arsenal was tinkering with a problem nobody had asked him to solve. His name was Walter Stanley Kowalski. Kowalski was 41 years old, a former auto plant toolmaker who had joined Chrysler before the war as a jig and fixture builder, one of the anonymous craftsmen who built the steel frames and molds that held tank parts in place during assembly. He wasn't an engineer, didn't wear a tie, and didn't have an office, but he was something far rarer. A man who understood the behavior of metal at an instinctive level. Years of working on auto body panels, aircraft frames, and now tank armor had given him a sixth sense for how steel moved under heat. He'd watched welders struggle for months with the turret ring issue. Every time they locked the ring into a rigid jig and began welding, the heat from the torches would cause the steel to expand and warp. but the clamps holding the ring in place didn't allow it to move. When the metal cooled, it contracted unevenly, and by the time the job was done, the turret ring had twisted itself out of alignment. You could machine it flat again, but that took hours, sometimes days, and destroyed production flow. Kowalski saw it happen night after night. The jigs were designed to fight the metal. He believed they should work with it instead. So, on his own time, during off hours when the plant floor was quiet and the machines were still cooling, he began sketching a radical new jig design. His idea was simple, but revolutionary. Instead of clamping the turret ring tightly to a fixed plate, his jig used spring-loaded supports that allowed the ring to float slightly as it heated and cooled. The springs absorbed the movement, letting the steel expand naturally during welding and then settle back into perfect alignment as it cooled. He added vertical guide pins to keep the ring centered, but left just enough freedom for the natural thermal motion of the material. He called it a self-aligning jig. His foreman laughed. His supervisor warned him to leave engineering to the engineers. But Kowalski wasn't looking for approval. He wanted proof. Late one night in August 1943, he built his first prototype using scrap metal and discarded parts. It looked crude: bolts, springs, and spare steel plates welded together by hand. He mounted a scrap turret ring on it and performed a test weld. When the ring cooled, he brought out his dial gauge and stared in disbelief. The deviation was only 0.006 of an inch, well within Army specifications. He tested again. 0.004, then 3. It was practically perfect. When the day shift arrived and saw the result, the room fell silent. The turret, one that would normally have been rejected, rotated like silk on its bearings. Within 48 hours, Kowalski's design was being demonstrated to Chrysler's senior engineers. Within a week, Army Ordnance inspectors were there in person. They were stunned. What Chrysler's top mechanical engineers and the Army's own metallurgy experts had struggled with for half a year, this self-taught jig builder had solved with scrap parts and intuition. The Army immediately classified the design as restricted material and gave it a formal designation: Self-Aligning Turret Ring Assembly, JIG, Model K1. It was ordered to be copied and distributed to every Sherman tank plant in the country. By September, K1 jigs were arriving at Fisher Body, Lima Locomotive, and Pressed Steel Car Company. The results were dramatic. Almost overnight, rejection rates fell from over 12% to less than 1%. At Fisher No. 2, Morrison reported the lowest defect rate in the plant's history, 0.8% by October. The rework backlog vanished. The assembly lines began to hum again. The Army calculated that across all factories, the K1 jig saved roughly 18,000 man-hours a month, the equivalent of 129 full-time workers. Production efficiency jumped so sharply that without adding a single worker, America's tank output increased by more than 15% by the end of 1943. In the span of 3 months, U.S. factories went from building roughly 1,147 Shermans in August to 2,291 by November. 344 additional tanks a month. The Army could now meet the mounting demands of the North African campaign, the Sicilian invasion, and the preparations for the coming storm across Europe. Historians estimate that by the end of the war, Kowalski's little K1 jig indirectly enabled the production of over 30,000 additional Sherman tanks, nearly one-third of all the tanks the United States. Built during World War II, the impact was invisible but profound. The Shermans that rolled ashore on Omaha Beach in June 1944, that fought their way through the hedgerows of Normandy, that clashed with Tiger tanks in the Ardennes, that stormed across the Rhine. They owed part of their existence to one man's midnight experiment with springs and steel. And yet, like so many wartime innovators, Walter Kowalski never received real recognition. His name was buried in classified documents and forgotten after the war. He got a $50 war bond, a handshake from an Army colonel, and a one-line mention in Chrysler's internal bulletin. There was no patent, no bonus, no medal. When the war ended, he went back to building automotive jigs. His children never even knew what he'd invented until decades later, when declassified ordnance reports revealed the truth. But his contribution was real and immense. The K1 jig wasn't just a clever tool, it embodied a fundamental truth about American wartime industry. That victory wasn't just forged by generals or scientists, but by ordinary men and women who refused to accept good enough. The arsenal of democracy wasn't built on blueprints alone. It was built on intuition, on problem-solving, and on the stubborn belief that there was always a better way to do something. Walter Kowalski's story became, in time, a quiet legend in Detroit's industrial circles. Factory veterans would sometimes tell new workers about the man who made the turrets fit. To most, it sounded like a myth, a story too small to matter in the grand scale of World War. But for those who understood what manufacturing really meant, it was proof that the difference between chaos and order, between delay and victory, can sometimes hinge on a single man, a single idea, and a handful of steel springs. In the annals of war production, his name might never stand beside Oppenheimer or Turing or Kelly Johnson, but somewhere, deep inside the turret ring of a Sherman tank now resting silent in a museum, there's a piece of steel that fits perfectly. Because one man in Detroit believed he could make it so.